Assalamualaikum and good morning. Today our group 18 will present the CFD project, which is to study the effectiveness of microjets in a sudden expansion CD nozzle. The introduction. A convergent-divergent nozzle, CD nozzle, or what they call as the Laval nozzle, is an hourglass-shaped tube that's squeezed within the center. It changes over the thermal energy of the stream into dynamic energy to speed up a compressible liquid to a supersonic speed within the actual course. CD nozzles are used in a variety of steam turbine and rocket sports. Supersonic jet engines utilize it as well. The problem statement. Most building issues such as the vehicle experience sudden development at the base, such as at the base of aeroplane with fuselage. The base drag accounts for more than 60% of total drag at transonic Mach numbers. As a result, the analyst must, depending on the circumstance, keep up control over the base pressure. To achieve near zero base drag, the base pressure from outside streamline future should be close to the surrounding pressure. Even so, the base pressure in combustion chamber must be lesser to ensure effective fuel air blending and combustion. This project was attempted with this thought in mind. Using a finite element strategy, the viability of microjets on wall pressure dissemination with sudden expansion in a convergent divergent series, or with sudden expansion was investigated. The objective of this project is first to design a expansion convergent divergent nozzle by using ANSYS Fluent software. This project also is done to assess the impact of microjet control that used in CD nozzle and to utilize the CFD strategy to quantify the stream field along an abruptly extended CD nozzle.
After discussion, we all agreed to make the sketching in 2D illustration by using ANSYS Fluent software, like we can see in this figure. All the measurement for this demonstration will be in millimeter. Like we can see from this figure, there are three main parts for this design, which is the convergent section, divergent section, and also the expanded duct. For the convergent section, this is the section where the subsonic condition will occur. The inlet or the convergent section diameter will be 30 mm and the convergent section length will be 40 mm. Next is the throat where the sonic condition will occur. The throat diameter will be 6 mm. The next main part is the divergent section. The divergent section is where the subsonic condition will occur, and we set the divergent section diameter to be 15 mm and also the divergent section length will to be 20 mm. For the expanded duct, we set the diameter for the expanded duct to be 21 mm and its length is 120 mm. Three boundaries have been set for the CD nozzle without microjet control, which is the inlet, outlet, and also the walls. While for the CD nozzle with microjet control, they have the same boundaries with additional one, which is the microjet. After performing the meshing, this is the result of mesh that we get from the ANSYS Fluent software. The inlet is set to be at the convergent section of the nozzle, and the outlet is set to be at the end of the duct. The other line from the sketching is set to be the walls and also the microjet. The density-based solver is applied to the general setup, and steady-state conditions are used for the simulation. For the setup model, the energy is used and the viscous is set to be standard Ka. The fluids material setup is configured to have an ideal gas properties, pressure inlet type and pressure outlet type. Boundary conditions are specified for the inlet and outlet respectively. The total volume is set at 101,325 Pascal for the inlet and 2,840 Pascal for the outlet.
So for the result, when we look at the velocity streamline of the convergent-divergent nozzle, we can see that with the usage of the microjet, it can help to reduce the recirculation formation in the suddenly expanded duct. Without the control from the microjet, the recirculation formation in the suddenly expanded duct zone is more notable if it has been compared with the microjet control. This result makes it clear that the microjet regulate the development of the weight at the region of the sudden expansion, which causes a decrease in the base pressure. For the pressure, we can see that the distribution of the pressure differ for each zone, including the convergent, the throat, the divergent, and the enlarged duct in the CD nozzle.
Continuation for pressure part. The figure shows the sudden expansion region for CD nozzle without microjet control had a high concentration of blue color when compared for CD nozzle without microjet. This results in high value of base drag in sudden expansion region for CD without microjet control. Next is the Mach number. From the figure, it is discovered that the trends are in opposition to the pressure contours. The Mach number is suddenly increasing at the region of sudden expansion after leaving the nozzle and flowing through the wall, and then it is suddenly decreasing when it reaches the duct's exit portion. The decreasing in Mach number in the exit portion is more significant in the CD nozzle with the microjet control.
This study, we managed to see that by appointing the microjet as control for that CD nozzle, it managed to reduce the base drag that accumulates in the sudden expansion region. This means that the wake formation is reduced by appointing microjet as control for the CD nozzle. From this study, we managed to design a sudden expansion convergent-divergent nozzle by using ANSYS Fluent software. The effectiveness of the microjet has been demonstrated and is shown in the contour diagram, which divide into three important results, which is the velocity streamline, pressure distribution, and the Mach number. From this study also, we managed to utilize the CFD strategy to quantify the stream field along an abruptly extended CD nozzle. Thank you.